My quest to come up with a video, one video a day for 30 days, I sometimes have to do things kind of quick and come up with something pretty fast, and sometimes explain some concept that I don't have time to make a really good copy of it. But I figure but some of these things are ideas I've had, and so there's some of these so I think I decided basically in some of these just to come up with something that was kind of like a rough example of something, and maybe later on I can come up with something better, hopefully, if it gets some traction. But anyway, yeah, for something like this, it probably would be a better video if it had like nice graphics and like I write it out as a script or something. I mean, I've tried to make videos like that. I've done a few like that, but problem is like it'd probably take me forever to get those done. And there's a bunch of ideas I had where I thought like, oh, I got to wait until I come up with the perfect way of doing it or something before I can release it. But then I figured like nothing was ever getting out. So I figured I might as well just come up with like what we call like a beta copy, a rough copy of some of these. And if some of these do really well, then I could try to like do a better one in the future. And we were talking about psychology, and this is going to involve like some math and stuff, so it's kind of interesting. So just from the only thing I'm going to say about the greater theme of this 30-day challenge was like the idea of abstraction, that there's the beauty in abstraction and like equations like this. And I'm not saying this doesn't look really good right now, and couldn't find a pen, and all I had was like this paint pen on me. So anyway, so this is what you call the rough stuff. So anyway, yeah, just going to talk a little bit about thermodynamics and a few equations for nomads. And I know this is not, there's a lot of people out there, and I know most people haven't even taken courses like this, like I've taken, or some have. I'm not insulting the public saying that but a lot of people aren't, and so they might find this like, what the heck, and I've, never really seen much of this. I think the only thing I saw that was a little bit it was at James Wonderlust Estate once. I saw him because he was a chemist, and he was trying to explain something about the chemistry of batteries, like using atoms and stuff. And I don't know if it went over very well or got many views, but that was like one example of some guy who had a lot of knowledge of something, trying to bring like the knowledge down to like the VanLife community, because let's face it, like none of us if I just put something about physics or math, there's going to be a million of those, and so I'm not going to get views. But if I try to say, okay, I'm going to try to focus just on the idea of VanLife and thermodynamics, I might be the only one, but also the only one who watches it is me, or maybe my mom. So anyway, got to start sleeping here. We're at the McDonald's here. Anyway, so let's just talk a little bit about the idea of thermodynamics, and I guess in this case we'll just talk about keeping your vehicle warm during the winter. And then so just look at this now with a lot of equations in physics. They're kind of true under certain constraints, under certain conditions, but you can say these are the type of things that are going to probably be true most of the time. So all right, so let's just say like heat loss, okay? So hopefully most people realize that heat flows from a hotter object to a colder object. So if you're in a warm van here, the heat's going to flow to the outside. And I guess you might also realize that you're going to lose a lot more heat, and you're going to have to spend a lot more energy on your buddy heater or whatever kind of heater you have, electric heater, diesel heater, if it's a lot colder outside, if there's a big temperature difference. So that's why not especially heat loss is equal to K, some constant, temperature in minus temperature outside. And now the constant, that's something that's going to be harder to figure out, but it's kind of a general thing that that we're saying is true of many objects like this. Now there is going to be a difference. Now I guess this assumes maybe there's not much wind too. The wind will speed things up, will also affect the thing too. But I should add here that heat loss is also known as power, and it's in units of energy over unit time, which is usually in watts, which is the same thing as joules per second, where joules is a very small unit of energy, or BTUs per hour. And then in electricity, the same units, power equals current times voltage, also gives you watts. And by the way, since it is energy per unit time, whenever you hear someone say something like watts per minute or something like that, or watts per hour, that's completely wrong, because it's already got the time built into it. Well, I mean, anyway, let's not get too complicated. Anyway, but this is just a basic equation. It does show you, right? So heat loss, so basically you could rewrite that equation like the energy that I'm putting into the amount of energy or fuel burnt or whatever, by creating inside my vehicle is going to be some constant. We don't know what the constant is, and then times this temp. But then if you just say but without the constant, you can just say okay, so if you double the distance, you'll see that you can easily see with this equation, if you just wrote out a few things, which I guess I'm not going to do here, that if you actually put in instead of T inside, you put 2T inside, that the heat loss is going to be twice as much, no matter what the constant is. So that shows you, if the temperature makes a big difference. And then, all right, and then you can just say here, and then if you want to just think about the idea maybe about using insulation. Now we know in a van or something like that, it's going to be a weird shape, but you can maybe kind of estimate if you can figure out the width at each point, of the how much, the R value, and then if you had to cut it down, you'd have to put that in the calculation. But basically, if you add up all the R values from every plate, okay, so each different piece of, like, let's just say it's like a big square that you're inside like a building or something, and then, okay, so each piece of this polystyrene foam that goes on stuff, each surface is going to lose an amount of heat, okay? So there's going to be 6 different surfaces, right? And then, so you have to add up each surface, but on just one of these surfaces, let's say you have just one of these pieces of polystyrene, then it's going to be heat loss is going to be T in minus T out divided by the R factor. And, and then, so in this case, it turns out that in this equation, that R factor is like 1 over K for that. Well, it'd be adding it up to, but anyway, but the R factor. So this doesn't come as any. So this shows it. So if you have twice as much R factor, you're going to have half as much heat loss, is the basic idea. And also, well, if you also were to put this into an equation where you use some other thing instead of R factor, and then you put in the width of the thing, then basically if you have the same type of material and you increase the width you double the width, then it's going to be half as much heat loss, more or less, Yeah, if someone really wanted to estimate like the heat loss in the van, they'd have to go to each spot where it was a different depth. And well, basically, though, you do know that basically, okay, if you have a piece of R14 or whatever it is, and then you cut it exactly in half, now it's going to be R7 instead. So it's, and then it's actually, when you look at this, is sort of like an example of kind of like the magic of the equations, because it kind of shows you that as you keep adding more and more insulation, you could basically get it to where you could stay warm just using your body heat. I mean, there's going to be some practical limitations, are you going to have not a squares to move around in your van, but it kind of does show kind of the magic of how you can what adding this material can do. So, so there you go. That's the equation you need for an R factor. Oh yeah, I did. If you go back to one of my old videos, maybe I'll try to put a link to that. There is a part where I talk about the definition of R factor. So yeah, it's anyway. But with any of these equations, you got to and I'm being simple here, but these these factors and stuff, they can all be written in different with different constants using Fahrenheit, Celsius, BTUs, or BTU per hour, or watts. And so anyways, to get it right, because usually with heat loss, we like to put it in terms of watts. So at some point, I think I did the equation where you can put in the R factor numbers and then get it in watts, because watts is what we really need to know, is how much. I just made a big mistake here. If you look at this equation, I should have put area in there. So you have to also, besides dividing the temperature difference by R factor, you have to also multiply the area in square feet, as you would expect. And then if you look below, here's actually the units that R factor actually means in English: foot square, Fahrenheit, times H, hours, but divided by BTU. But the most simplest equation, if you want to look at this, if you want to, for your own purposes, you just have to do power loss in watts. It's going to be area in foot squares, square feet, times temperature difference, divided by the R factor times 5.678. Maybe I'll have to do a whole equation. I'll have to do a whole video just talking about that equation, And then you can even then you can even figure out things if you rearrange this equation and the R factor, or if you know the K, you can kind of figure out, if my body puts out 100 watts of energy approximately, then how hot is it going to get inside? How much of a difference? I mean, like I said, a lot of these equations, once you actually do it, you're going to find there's a lot of stuff, because it's going to matter a lot, whether there's also a lot of air loss and that sort of thing. But we're just saying, okay, yeah, this is the basic equation under a pretty basic situation where there's not a giant difference in heat between the hot and the outside, and also things there's not maybe a lot of wind, and also there's not a lot of heat, because it'll throw the equation off. It's it doesn't matter what that equation says. My windows are open. I mean, there's a lot of heat being lost a lot quicker than it could be lost through just conduction. But in this case, I'm trying to keep it cool because it's the summer. But right now, it'd be a little more difficult for me to talk about the winter stuff. Well, basically, okay, if you just want to do this, one thing in math and physics is the sign matters. So if you actually, let's just say if it turned out like that, it was actually colder inside than the outside, then this whole thing would end up being like a, oh yeah. So the way it is written right now, you can see that if I were to put the actual numbers that I put, like, if it was a winter time and I put in like, 60 and then put in 70 outside, or no, I put in like 70 inside and then 60 outside, so that would be 10. Okay, so that's, but then if I reversed it, it would be a negative number, and what that would mean is actually that if we're saying that heat loss, if you get a negative number, it means it basically need air conditioning. Okay, all right. So anyway, all right, and okay, so we'll keep going since I'm to like to anybody who is still listening. It's like to my imaginary class. I'm Professor John here. Okay, but but if you want to get into a little more complicated stuff, there's actually an equation here, dd dt. Well, basically, you get some equation. This part is definitely a part you don't have to know, but if you just happen to be interested in this sort of thing or already know it already, then enjoy. In here with like this exponential E thing, and basically you'll get like this chart showing like this is like how the heat, this is how much heat is left with, how much thermal energy is in an object, or this is what the temperature will be over time. And the interesting thing is that according to this equation, it doesn't ever actually make it to the outside temperature, but it just keeps getting slower. So you can see this though. This is actually called Newton's law of cooling, and it can be used for lots of practical things, including determining the time of death by finding what someone's temperature, knowing like approximately how fast someone's body temperature is lost after they die. So that you'll definitely lose a lot more energy, like when there's a big difference in temperature between the inside and the outside, as you'd expect, right? Because then there'd be like, no limit to like how much you could heat a thing or something if that wasn't the case. But anyway, all right. Well, I hope that was understandable. I mean, I know most of these videos are going to get like 2 views, but anyway, you never know. I just kind of put this stuff out there. It'd be nice if someone says, "Oh yeah, that's really interesting." Maybe in the future you could do a better video that's explains this. Because right now I'm just like, okay, this is maybe just a diary of, maybe my YouTube is just becoming a diary of all the thoughts I had that are probably never going to make widespread. Or maybe I'll be a legend after I die. No, I don't know. Kind of nice. Look at this wind here. On a side thing about thermodynamics, might be another one to think that a lot of people don't know the difference between temperature and thermal energy, or they don't know. They don't understand the difference between, let's say, like wind chill and temperature. Well, basically, yeah, maybe I don't want to get into that too much, but basically the idea is that like once 2 things are at the same temperature, there's not going to be any difference in energy flow between them. So like, let's just say the wind. So the wind cannot get an object any colder than whatever its temperature is. Now it can actually get a human being colder than colder than the actual outside temperature because of the evaporation and stuff like that. But anyway, temperature is the thing that it's the quantity that determines if 2 things are in equilibrium. So I guess that's one of the simplest explanations of what temperature is. It's a little bit tough to explain that to people sometimes, but it's anyway, yeah. So anyway, all right. Well, that last part wasn't probably too like understandable, but anyway, all right. Well, I guess I'll get going, and then at the end here is what my plan for this 30-day series is. Although I've just been barely actually keeping to that, but anyway. But in case anybody, this 30-day YouTube mini-series is a psychological experiment using Jungian psychology to live better and experience more this summer. I'm not a psychologist, just a layman looking to apply Jungian principles of life. I'm starting with the idea that the unconscious mind is very smart and tells us things. And believing in this, I drove up to Hibbing, Minnesota, and I found that 4 locations in Hibbing, Minnesota corresponded quite well to 4 different principles called the Hibbing Fraternity. The first one is the Hibbing Ghost Town, which the characteristics is you feel the echo of the past as the wind flows down established paths. This represents unconscious voice being in the center of a moving circle, the mother archetype, home, center, castle, etc. Character I'm coming up with here to explain it is Nellie, the ghost sheepdog mom who circles the area, protects and guides. The Greyhound Museum has to do with travel and also the Jungian idea of beauty as a way of mentally feeling your way into physical objects and flowing into life in general, flowing beauty, mentally becoming part of the object. The character here I'm coming up with is Flows With It, which is a Native American cartoon character who has a magic canoe, finds all past, glides over, portages, flows into life. Now the ore pit, it represents the smallness of the individual, abstraction, and the way in making the world simpler, more understandable, connections, the beauty of symmetry, the beauty of maps, beauty of mathematics. And this is supposed to be Laser Nash. Doesn't look like him that much, but anyway, it's like John Nash with his cup sending out all these laser beams across, dividing the world, trying to find that order in the chaos from A Beautiful Mind. If you haven't seen that movie, Bob Dylan's Home. It represents stories, archetypes wishing to become someone else. DJ Hat Trick, what he does is he gets people into the groove by putting different hats on and sending people into different paths. It's sort of like the way we do whenever we listen to a song, for example. Here's a simplified view of the quaternity here that I'm going to be using for this 30-day adventure. And this is what it's going to more look like. I'm just going to do a simple sketch that I'll put in the video and then just kind of explain it like on a notepad like this to make it simpler so I can get it done. So I can do a video for 30 days. And so subscribe to get all 30 of those videos. If anybody's interested, you can look at this last part or just feel free to skip it.